Yeah, we are disallowing unmute for, I think the way, so we're gonna, if you raise your hand, then we'll unmute you. But I'll go over this. Yeah. Pulling in. All right, I think maybe it's a good time to get started. Hello, everybody. Welcome to our second joint webinar. So this is a sub-initiative of the IMS New Researcher Group. You can go online to read a bit more about this new researcher group. I highly recommend you to kind of join or think about joining. This is a joint webinar with the Young StatS group that has been running for a while, as well as the Young Data Science Research Seminar at ETH Zurich. That's also been running for a couple of years. So the first seminar was on distributional robustness and causality. This one will be on algorithmic fairness. We have three wonderful speakers, or two wonderful speakers and a wonderful discussant. So the first speaker, I'll just introduce them a little bit so that you know. The first one is Linjun Zhang. He is an assistant professor in the Department of Stats at Rutgers, and he received his PhD in statistics at UPenn in 2019. Our second speaker will be Mikhail Yurochkin. He is a research staff member at IBM Research and at MIT-IBM Watson AI Lab in Cambridge, Massachusetts. He received his PhD in statistics at University of Michigan. Our discussant will be Razieh Nabi. She is a Rollins Assistant Professor in the Department of Biostats Bioinformatics at Emory University and graduated from Johns Hopkins in 2021. So the way the format of the seminar will work is that we have about 30 minutes per speaker, so 30 minutes for Linjun and 30 minutes for Mikhail, and then something around 20 minutes for Razieh. You are free to ask questions on chat during the talk or after the talk. We'll try to bring these questions up to the speakers. You're also welcome to raise your hand if you want to ask your question yourself, and we'll just unmute you ourselves. This talk is recorded, if you notice there at the top. And I hope the format is completely clear. And if everything is good, I think we can get going with the first speaker, Linjun, who will get us started.
Okay, can everyone see my screen?
Yeah,
okay, great.
Perfect.
Yeah. Okay, so hi everyone. Thank you for coming, and especially thank you, Armeen, for this, for organizing this very nice seminar and inviting me to give the talk. So in this talk, I will share my recent research on trustworthy conformal prediction with focus on algorithmic fairness and distributional robustness. The talk today will be mostly based on my work with my two long-term collaborators, Cynthia Dwork, who is a professor at Harvard, and Zhang, who is her PhD student. So now let me start the talk and briefly motivate the problem. So as now we are in, say, the age of AI, or especially the AGI, machine learning tools have been widely used in many important domains in our real life. So, for example, in loan application, people use machine learning models to decide, say, if this person will default the loan or not based on his or her profile. And also, say, similar models are used in like job hiring and medical prediction. So, recently, say, because of the popularity of conformal prediction in statistics, people found that in addition to point estimation or point prediction, uncertainty quantification is also very important in those consequential domains. And in this talk, we are going to answer the following question. So can we have a fair and a robust uncertainty quantifications for those machine learning predictions? So let me give, say, a brief recap of what is the uncertainty quantification and conformal prediction first. So uncertainty quantification is a general topic, and conformal prediction is a framework that provides a way for uncertainty quantification. So at a high level, conformal prediction is a post-processing algorithm. Okay, so this framework will take, say, any predictor f hat as input, okay, where f hat will take, say, some covariate, for example, the profile of certain person, and predict certain outcome of this x. The f hat is any arbitrary given predictive model. And conformal prediction will post-process this f hat to produce, say, an interval c hat. And the c hat is guaranteed to have the correct coverage, okay, which means that given a new data point x new, the interval produced by c hat would cover y new with a desired probability. And the guarantee here is, say, the coverage probability would be quite close to the pre-specified desired probability 1 minus delta. This alpha simply controls this tolerance level. Okay. So this is the standard conformal prediction. However, I would like to introduce the two potential issues of this standard conformal prediction framework. The first one will be algorithmic fairness, and second one will be distribution shift. Okay. So I will introduce, say, those two potential issues first, and then introduce the solution. Okay. So, any question for now? Okay, good. So first of all, we will talk about the fairness issue of the standard conformal prediction. So first of all, if we look at the definition of the coverage, okay, we will see this coverage probability takes probability with respect to the marginal distribution of x, y, or take the joint distribution of x new and y new. Right? So this probability is an on average guarantee. And typically, an on average guarantee cannot lead to, say, meaningful solutions for all subpopulations. So for example, if you found a method that works for all patients in this area, okay, and the guarantee is, say, on average, then typically for those the small groups, for the groups of the white people or for the groups of black people, this on average guarantee will not work for those small subgroups. Okay, so mathematically, in order to define say, such a bias or fairness issues, in 2020, Emmanuel Candice's group introduced the following fairness notion in conformal prediction called equalized coverage. That basically this notion requires, say, for all protected groups A, the conditional probability, the conditional on X mu belongs to A. The coverage, the conditional coverage probability for all A should be quite close to 1 minus delta. Okay, so this is a fairness notion in conformal prediction introduced in 2020. However, a caveat is in the same paper, when the author proposed a method to satisfy this fairness notion, to satisfy this equalized coverage, their method would require the disjointness of A. Okay, basically, they assume all the groups in A are disjoint because their method is actually very simple. Basically, what they do is they divide the data set into different groups according to different values of A, or according to different membership in A. Then for each subpopulation, they simply apply the standard conformal prediction. And then they can achieve this conditional coverage. So very simple method. But because it's very simple, so it will require this disjointness. So the first question we would like to answer is, what if those protected groups are overlapping? For example, the race group and gender groups, they are overlapping. Or what if there are infinitely many protected subgroups? Okay. So in this case, how can we still achieve this fairness notion? So you may wonder, say, why will we care about this infinitely many group setting? Let me give you a few motivations here. So typically, in a standard machine learning literature, when people want to achieve a certain fairness, people will introduce or pre-specify those protected groups first. And given these protected groups, people then design or implement certain algorithms that achieve fairness with respect to those pre-specified groups. And so this is a typical approach. However, this approach has issues, and I will give you maybe two short reasons. First is maybe say some groups, they do not have say much power, and they do not advocate themselves such that the algorithm designer hear their voice. Okay, so if in this case, such a group will be ignored in the algorithmic design procedure. And secondly, in many settings, the groups will change over time. For example, the definition of race and gender will change over time as people's knowledge develops. And say if the definitions of groups change over time, then definitely if you retrain the algorithm every time when the definition changes, it's not very impractical. Okay. So in order to address these concerns, the algorithmic fairness community in the CS field, they try to define the groups by a set of classifiers. Okay, so instead of pre-specifying the groups, they define groups by a set of classifiers. So for example, they define fairness. They define fairness with respect to all groups that are identifiable by a logistic regression model with certain parameter constraints. Or say sometimes they define, say we want to achieve fairness with respect to all groups that are identifiable by a convolutional neural network with certain architecture. Okay. So such a definition captures most of the interesting groups we want to protect nowadays, including gender, race, age, etc. So if we define the groups in this way, then the number of groups will be infinite. Okay. And the previous method cannot address this issue. So this is the first potential issue of the standard conformal prediction. fairness. Now let me talk about the second potential issue, which is the robustness against distribution shift. So in many real data applications, the data is not very ideal. The test data has a different distribution with the training distribution of the data you have at hand. But still, people want to ensure a valid coverage for the test data for this new distribution. So in this talk, we will focus on the distribution called the shift called the covariate shift, which is a special case of the distribution shift. For this distribution shift setting, we assume the marginal distribution of X are different across training and test domains. However, the conditional distribution Y given X are the same between those two domains. As one example, say, if we want to train a neural network to classify cats and dogs, the training time, maybe you feed it in using those real life images. But in the test time, maybe the image you see are all those cartoon style image. So this is one illustration of this covariate shift setting. So how can we still guarantee valid coverage for this new distribution? So in order to address this covariate shift issue, actually in 2019, there is a work that addresses this issue. However, this work would require, say, the knowledge of the density ratio, the density ratio between P of X in the test domain and P of X in the training domain. So a natural question is, what if this density ratio is unknown or even cannot be estimated? Because in some cases, maybe you don't see any test data when you train your algorithm. But if you don't see any test data at all, then it's impossible to estimate this density ratio because there's no data at all. So what if this happens, and how can we still guarantee valid coverage for conformal prediction? And so this is the second potential issue we want to address in this talk. So now, given those two potential issues, in the rest of this talk, we are going to introduce a unifying argument that try to connect those two seemingly different goals together. And then we are going to introduce an algorithm that can achieve this unified goal. And we will also provide theoretical guarantees to our algorithm. Any questions or no? Good. So now let's try to unify those two potential concerns in conformal prediction. In order to do that, let's do some math, very little math. So let's first say recall what is the equalized coverage requirement. Okay, so this is the requirement. If we rewrite this requirement, okay, we'll end up with this equation. Okay. And similarly, okay, after some algebraic manipulation, for covariate shift setting, okay, the coverage probability can also be written as, say, a similar form. Okay, let me add some color. You can see it more clearly. So if we compare those two forms, you will see, both of them want to control certain expectation for a product of two terms. Okay, in those product, the first term are both the functions of x nu. And the second term are functions of y nu and x nu. And in this case, both of them are indicator functions. Let me be more specific. So for the two requirements that we want to satisfy previously, okay, both of them can be written in this form. Okay. So basically, for the red part, okay, we want to make sure that, say, for all the red functions in certain class, the expectation is below some threshold. And similarly for the covariate shift setting. Okay, so by observing this similarity in our paper, we come up with a generalized notion called S-happy multi-calibration to unify those two seemingly different goals. So there's a long history or long story say why we come up with this name. It has some connection to the multi-calibration notion in the algorithmic fairness literature. But for now, I will skip the long story and simply focus on interpreting this generalized notion we proposed. So first of all, let's see, so if we take, say, this C and S to be the special forms as we discussed before. Okay. Then this S-happy multi-calibration notion will recover the uncertainty quantification, say, under equalized coverage. Similarly, if we take C to be the density ratio, then this notion would recover the uncertainty quantification under covariance shift. Okay. So we use one notion to connect those two problems. And at a high level, okay, we can actually interpret this S-happy multi-calibration notion in the following sense. So first of all, we treat C as the auditors, and S can be viewed as certain risk measure. Okay? And our goal of this notion is simply to make all auditors happy, such that the expectation of the C times S is well below some threshold alpha. And we want for all C belongs to a certain class, okay, and this inequality are satisfied. And this means all auditors are happy. Okay, so this is the high-level interpretation of this S-happy multi-calibration. Okay. So given this generalized notion, we then introduce an algorithm called a happy map that can produce an algorithm or a predictor that satisfies this S-happy multi-calibration notion. Okay. So similar to the original conformal prediction, this happy map algorithm is a post-processing algorithm. Okay. It can take any arbitrary predictor F0, and after certain post-processing, it will produce an F, and we can prove the final output F will satisfy the S-happy multi-calibration notion. Okay. The algorithm itself is very simple. It's simply based on the idea of gradient boosting. Okay. So it's an iterative procedure. Basically, for each iteration, we found some unhappy auditor, okay, such that, say, this expectation is greater than alpha. Then once we found such an unhappy auditor, we perform an update according to this unhappy auditor, try to make it happy. Okay. Then after a certain number of iterations, we are guaranteed to make all auditors happy. Okay, that's all. And finally, after certain iterations, we will output the final predictor F. So our theorem basically says that if we want to make all the auditors happy, okay, with, say, the threshold level alpha, then the iteration number of this algorithm is at most 1 over alpha squared. Okay, so this algorithm is guaranteed to converge, and the final output is guaranteed to satisfy S-happy multi-calibration notion. Okay. So given this general result, then let's see how it applies to the two special cases we have discussed. Okay, the first is the algorithmic setting. Okay, so basically we want to achieve the equalized coverage notion we discussed before. Okay. So if we apply our general result to this particular equalized coverage setting, we will find that, okay, so after the happy map algorithm, the final output, the resulting prediction interval C hat, okay, will satisfy the equalized coverage notion, okay, for all demographic or protected groups A with a certain sample size assumption. Similarly, for the distributional robustness against the covariance shift, okay, our result implies that once the candidate set, okay, the auditor class C, okay, can approximate the ground truth density ratio with certain error tolerance, okay, beta. Then, as long as you allow, say, the algorithm run in a sufficiently long time, okay, such that you can make alpha small, then the distributional then over this distributional robust shift, okay, the coverage can still be guaranteed to be quite close to 1 minus delta. Okay, so this alpha can be arbitrarily small as long as you have a sufficiently large computational resources. Okay, and this beta, the approximation error, can also be quite small if you choose a large class of say the function class C to approximate density ratio. For example, if you take this script C to be a neural network with 3 layers and with some constraint on the width, then this beta can be extremely small. Okay.
Linjun, can I ask you a question?
Yeah, sure.
Like a couple of slides back about just the algorithm. I'm just trying to. It was a bit fast for me to understand what you're actually updating. So you're updating FT, right? And this function is just a prediction, right?
Yeah. FT
And
is a prediction.
CT is not being. You're also updating CT. I guess it's like the worst.
The unhappy auditor. Yeah, CT is the unhappy auditor, and CT is a function of X.
I see. So you keep doing it until you fall below alpha. I guess that's what you're saying. So as long as you
yeah.
CT.
Yeah, exactly. Until all the auditors are happy, such that say this expectation is smaller than alpha.
I see. So you're not really looking like this algorithm doesn't guarantee that you're finding. Yeah, I mean it'll make sure that it's less than equal to less than alpha, which is what you want. You're not necessarily minimizing this objective, right? Like you're not.
So what is the objective here?
The objective being what's inside, like the left hand side of the expectation of the C times S.
Yeah, we don't minimize that.
You're just finding like a feasible point or like a feasible an algorithm such that it's okay for every CT. And remind me just so CT here, so one value of C in this big C is just like it's like one particular group, right? Within your set of groups.
Yeah. Right.
I see. And sorry, one more question about the theory. So is there any sense of like if the overlap between the groups is large versus small, how much harder the problem becomes?
The overlapping doesn't matter. Only the cardinality or the complexity of the C matters.
Okay.
Yeah, so our result, the sample size would depend on the complexity of the C.
I see. Okay, so the previous results, the paper that you mentioned, it was just because their algorithm could only handle disjoint groups. It wasn't something fundamental about the challenge of kind of groups that share a lot of similarity versus not.
Yeah, exactly.
Okay. Cool. Thank you.
Thanks for the question. A quick note is that actually we don't need to minimize this say objective function once we specify alpha. So if you really want a very tight control, say, or very accurate coverage probability, say the coverage probability is super close to 1 minus delta, we simply choose a small alpha. That's enough. So we don't need to minimize the whole quantity. If you want it to be close, then we pre-specify this alpha to be very small.
But I mean, yeah, okay. So related to that, so you kind of want like your coverage to be as your interval to be as tight as possible, right? So
yeah. Later we are going to introduce a result on the interval length, but for now let's focus on the coverage first.
Okay, but so I guess if you want to minimize the interval, then like you want it to be as close to alpha, I suppose, right? So you don't actually really want it to be much less than alpha.
Yeah, exactly.
Too conservative. Okay.
But this alpha is slightly different from the standard language in conformal prediction. So here the desired probability is 1 minus delta. Alpha is simply an approximation error. Okay, cool. Yeah, so we have similar result for correct shift. Okay. Then here comes Armeen's question. Sometimes in addition to caring about the coverage, we are also interested in the conformal prediction interval length. So here we are going to introduce a theorem called the no-harm theorem. So in order to introduce a result, let's introduce a few more notation first. So first of all, let us denote the F delta star. as the delta quantile function of y given x. Okay, and in addition, we assume say y given x is symmetric. Then under this assumption, the shortest 1 minus delta prediction interval that satisfies the equalized coverage will be this C star. Okay. Then our theorem says that if the initializer C0 is quite close to C star, here this delta is a fat difference. Okay, so if the initializer C0 is quite close to C star, then the final output C hat will still be quite close to C star in terms of the interval length. So this result tells us that our post-processing algorithm does no harm to the interval length. So if the initializer is good, then we will preserve these benefits. And in other words, say if this say initializer is not too good, but still say the interval is upper bounded by say some number, then the final output will not be too long. So it will not destroy the information given by C0. So for example, if your C0 is say carefully constructed using some standard conformal prediction, typically it has certain nice property. And our algorithm will not destroy those nice properties preserved in C0. Okay, okay, good. Yeah, then let me quickly conclude this talk. So in this work, we introduce a generalized notion called S-happy multi-calibration to somehow quantify the potential issues in the conformal prediction. Actually, our notion is more general, and we also propose an algorithm called happy map to achieve this S-happy multi-calibration notion. So as I mentioned, this is a general framework. So in this talk, we only cover its application to the algorithmic fairness and distribution shift. Actually, there are more applications available in our paper. So for example, we can also use this framework to address the accuracy transfer issues in transfer learning and moreover the mixing data analysis. So if you are interested, please check out our paper available on arXiv. So I will stop here and thank you very much for your listening.
You, Linjun. Nice talk. Any questions from the audience before we move to the next talk?
Maybe I could start with one question. So thanks, Linjun, for the nice talk. And I'm wondering the covariate shift setting. So you have the density in the theorem, you have the density ratio between
yeah. We do have so we do have an additional assumption on this. We need to assume a density function of y given x is upper bounded by some universal constant. So this is this assumption is not needed, say, in the existing literature, but we need this in our work. But in terms of density ratio, we don't have explicit assumption. We only
but
need,
at least the density ratio needs to be well defined, right?
Yeah, it should be well defined and it should be well approximated by the script C. So if you choose, say, for example, please go ahead.
So the distribution for X in training and in test should have the same support. So
same support or good
because
question.
Otherwise it would be either zero
indeed.
or infinity.
Yeah, indeed. Yeah, we require them to. So yeah, this density ratio should be well defined.
Okay, I see. Do you see any potential to like generalize this to the case where you actually have different supports for test and training distributions?
So this boils down to say this algebraic massage. So basically, we rewrite the coverage. Let's see. So basically, we rewrite the coverage under the new distribution by this equation. And so when we rewrite this, we implicitly assume, say, this distribution is well defined. But as you mentioned, maybe it will go to infinity if the support of X chain is less than or smaller than the test distribution. In this case, I would think let me, maybe I had a typo here. It should be P train over P test. Oh, no. P test over P train. Yeah, that is correct. So in this case, what should we do? If it's, I was just wondering if we can discuss case by case, say divide the support by two parts and then rewrite the formula. Yeah, I think it's a good question. We'll think about this. Yeah, but my naive idea is simply say we divide the support into two parts. And for the well-defined part, we use the similar trick. For the say not well-defined case part, where it's simply 0 or something. Or a constant.
Okay. Thanks for the comment.
Thanks for the question.
Just if there is still time, or just one additional question. I missed the initial part due to some technical things, but is this possible to study this algorithm in terms of asymptotics and how in terms of mathematical?
Oh, asymptotics. So first of all, say our result indeed require a sample size condition, but which is different from the standard conformal literature. So basically, all the methods there will hold for arbitrary finite samples. Here we need a certain lower bound on the sample size. But this cost give us some gains. Say, for example, in the correct shift setting, we don't need to even see the data from the test domain. So we lose something, but we'll also gain something. Then in terms of asymptotics, I think it will be maybe an interesting direction, say, trying to analyze if this dependence on the dimension and alpha is tight or not, n goes to infinity. I think this is a great question. Maybe this optimality is something we need to consider in the next step. Thank you for the question.
So we have a raise. Oh yeah, there you go. So Fanny, you can speak.
Okay, thanks for the talk. I'm still a bit confused. That's just following up on Armeen's question. So if you go back to the algorithm, right? So here you mentioned something about gradient boosting. I'm just missing a little bit, like, why would FT minus eta CT, why would that decrease the CT? Because in the end, you want all the CTs to be small, right? Or at least CT times S. And so why, you have some assumptions on the...
we don't have any assumptions, but I can give you some intuition, say why this algorithm works. So basically, as we mentioned, the S is a certain general function. Right? So actually in our proof, we view this S as certain gradient of some potential function or loss function. Okay. So basically, this algorithm is trying to optimize that the hypothetical loss function, where S is a gradient of that hypothetical loss function. Okay. Then this algorithm is similar to gradient descent in the sense that if, say, the inner product between C and S is greater than some alpha, this means the direction of C and S are somehow aligned. So then if we update the algorithm, say, using the direction of C, then it can minimize that hypothetical loss function. And therefore, the algorithm will converge because the potential loss function will always decrease when we iterate.
Okay, and the potential loss function is related to the final, I see. So then I see, okay. So basically you kind of say that your gradient goes towards, like C goes towards stationary point or something, like you have the gradient is small or something. I see.
Yeah, exactly.
Interesting. Okay, thanks. Yeah.
Thanks for the question.
Okay. Thank you for the questions. Maybe it's good time to now switch to Mikhail.
Right. Well, yes. Thanks for the great talk, Linjun. Okay, so let me share my slide. Okay, so my talk will be about individual fairness and kind of with a focus on how to make it useful in some practical applications. So we'll start with a simple case study. So it's just a sentiment analysis task. So we want to classify words as positive or negative. So positive words are admire, and negative words are something like aggressive. So it's a very kind of standard NLP task. So it's also a very simple one by today's standards. So we can use, some simple neural networks and word embeddings, and it's pretty straightforward to get 95% test accuracy on a laptop. So the question is, okay, so is this now a good enough predictor of a sentiment of a word? Well, the accuracy is good, but if you try to deploy a system like that in practice, so, to review maybe like a product reviews, or movie reviews, and so on. So it might encounter some names in text. And we didn't really train it on names, so it's not very clear how it will react to them. I guess ideally we would hope it doesn't affect the sentiment. And so to check whether this is true or not, so we'll consider the set of common European American names. So for example, Adam and Ryan, and the common African American names, such as, let's say, Alonso and Terry. And so we can simply plot the sentiment score that the algorithm assigns to these names. And we can see that, so if you kind of group them by race attributes, so to which they are more typical, we can see that there is a pretty big difference between, let's say, average sentiment scores that Caucasian, names typical for Caucasian population receive and names typical for African American population receive. So this could be seen as a violation of fairness, even without kind of going into a specific definition. So we can use group fairness. So here it's a simple kind of group fairness approach, demographic parity, which says, okay, we want the names, if you have protected groups, so we want the average outcome for these different protected groups to be the same. And so here it is satisfied, but let's say for Tyree, for instance, this wouldn't appear like the algorithm is still fair because their name would still receive a very low sentiment score in comparison to a different name such as Ryan. So we can see that we kind of have we satisfied one of the group fairness definitions, but it didn't quite address the sort of more intuitive notion of fairness for an individual here. And so to handle, such kind of problems, so we will talk about, okay, so first we'll start with a definition of individual fairness. So what does it do, and see how can it address problems like that, and also some other ones. So the main idea of individual fairness is that we want the algorithm to treat similar individuals similarly. So this can be formalized with a kind of a Lipschitz continuity kind of condition proposed by also Cynthia Dwork and co-authors in 2012. So there are a couple of things going on here. So first we have a machine learning model H. And so on the left-hand side, we have this dy. And so we compare the outputs of our model on two inputs, x1 and x2. And so dy just simply measures how similar are those outputs. For example, in classification, is the prediction the same or not? And so on the right-hand side, we have a dx. So dx is something we call fair metric. So it measures similarity between inputs. So for example, if x1 is distrust and x2 is nice, then those two are dissimilar. But if x1 is Ryan and x2 is Tyree, then we would want the dx to be small, so because those are similar. And so we want it to be satisfied for all x1 and x2. So then we say, okay, for similar individuals such as x1 and x2, they receive similar predictions. So if you try to enforce this definition in our earlier applications, so we can see that we can actually achieve very similar sentiment scores for all of the names that we considered. So this would mean that we basically satisfy individual fairness. So in this case, we also pretty much satisfy group fairness, which in general does not need to be the case, but here it happens. So in terms of accuracy, it also doesn't need to necessarily hurt our algorithm too much. So here we managed to achieve it by only losing 1 point of accuracy. So to motivate a little bit the definition of individual fairness, so it actually is something that, I don't know if it was the inspiration for it or not, but something very similar conceptually was done back in 2004. So there was a celebrated study of the racial bias in the US labor market. So this was done, outside of machine learning or algorithms. So it was pretty much done manually. So the investigators responded to job ads in Boston and Chicago newspapers with fictitious resumes. So they basically wrote them themselves. And so there were some template resumes that they used, and they assigned different names. So the resumes were the same. The only difference was the first and the last name. And so they assigned either African-American or white-sounding names to these resumes. And so then, they applied for jobs, and then they concluded that there was a pretty large amount of discrimination against African-Americans because the resumes assigned white-sounding names received 50% more callbacks for interviews. So this is essentially like, manually checking individual fairness in the real world. So we create pairs of similar individuals, and then we check whether they receive similar outcome or not. And so in this case, we don't even have a machine learning model. We kind of the world is a model in this case. So going back to the definition of individual fairness, so why don't we perhaps use it more often, or why maybe it's not as probably if you work on algorithmic fairness, you for sure heard about group fairness. Individual fairness is sort of somewhat less well known, I would say. So what are the difficulties here? Well, so the first difficulty is that enforcing this kind of Lipschitz constraint is not very easy, especially if you work with neural networks or like some complicated models. And so the second one is probably the biggest elephant in the room is the fair metric, right? So how do we know if two individuals are similar or not? So we need some way to decide on that, and that seems pretty complicated. So in order to make individual fairness practical, we need to address those problems, and we'll start by discussing how can we learn individual fairness metric from data. So instead of manually trying to hook up a function, and then so once we have it, so we can quantify individual fairness violations. So to what extent that Lipschitz condition is violated, and then we can see if we can correct those violations. Okay, so starting with the fair metric. So of course, manually writing a function could be very complicated, although, something very straightforward, such as like, if the race is the same, then they're similar. If it's different, they're dissimilar. It's certainly possible as a manual fair metric, but it pretty much reduces it to group fairness. So here we'll try to learn some more sophisticated fair metrics. So, and we'll consider 3 sources of data. So there could be samples with protected attributes, which is common in census data, then groups of comparable samples, where we just have, like a collection of data points, which we believe all should be treated similarly, like say the names. And then there also could be pairs of comparable and incomparable samples. So in this talk, I'll focus on the first 2. And so in all cases, we will learn this fair metric in the form of the generalized Mahalanobis distance. So essentially, we'll be learning this metric sigma in the middle. Okay, so starting with samples with protected attributes. So this is convenient because it's, at most of the data sets, let's say we use for, testing fairness algorithms, they usually have those. So a lot of census data has it. So here, what we can do is we can learn what we call a sensitive direction. So we can train a logistic regression to predict, for instance, the gender of an individual. And so we can so once we have this direction V, which is the direction orthogonal to the decision boundary, so we can ignore the differences, that align with this direction. So we essentially project it out. And so here, we can do it for more than a single protected attribute. So we can construct the set, as many as we want sensitive directions. They form a subspace, and we just simply project it out when comparing the 2 individuals. So a simple illustration. So for the sake of illustration, the gender is binary here. So we have some 2-dimensional toy data. Then there are some, women, there are some men. And so we can fit a logistic regression model. So it will look something like this. And so now we can project out this direction. And so this will basically lead to something like this. So where, the distance between men and women is essentially a lot smaller if they differ only by the gender. But there's still some differences along the other data dimensions. Okay, so the next example is a group of comparable samples. So that might sound a little bit more mysterious at the first glance, but actually we've already done it in this talk. So we use this technique to train that sentiment predictor. And so what we did is we collected the word embeddings of popular baby names. We didn't need those names. We didn't anyone, to make a judgment whether this name is popular among, one race or the other race or anything like that. We actually just downloaded a data set of popular baby names in New York City. We didn't need to know their gender because also the same names can, of course, be assigned to different genders. It's simply just a big list of names. And so because we believe that all names should be treated similarly in this application, so we consider it as a group of comparable samples. So the idea is quite simple. So if we have something that we want to be treated comparable, so we want to make sure that the distance between all those data points is small, well, we want to get rid of the variation in this data set, right? So, and we can learn the directions of major variations using PCA. So again, we construct those, the set of sensitive directions. And again, we just project them out when building the FAIR metric. And so this results in a sort of a new sigma, so that it can use now to compare different inputs. So again, just so because the PCA learns these directions of major variations, so now the distance between any pair of names after projecting out those directions will be very small. So this is kind of what we wanted to achieve, because we wanted that group of samples to be comparable. So to motivate it a little bit with a factor model to explain also where they come from. So suppose we can think of our data after some embedding transformation. So if it's text, we can use word embeddings, we can use sentence transformers to embed the data. So we say that, okay, the embedding space is approximately sort of decomposable in the form of a linear model into some protected features times V plus some relevant features times U. So protected features is something that we want to, we want to make sure those are ignored. So we don't want to discriminate upon them. And relevant features is something that actually may be useful for an application, like a person's year of experience and so on. So the algorithm is pretty simple. So if we center a group of comparable samples, so we basically, get rid of the relevant features because they're comparable, meaning that the relevant features should be similar. So they basically, get canceled out after centering. So now we just end up with this, and we can, do like a simple SVD decomposition to learn V and then ignore it when building the FAIR metric. So this is same as the PCA idea. Okay, so next is, so now that we have a FAIR metric, so we move on to the next step in our problem, so which is how do we train FAIR models. So here we will assume that the FAIR metric is given to us in the form of some function that takes x1, x2 and produces some number, positive number. So the key idea here is the connection to adversarial robustness. So just to recap quickly, so the adversarial, the idea of an adversarial attack is that we can change model prediction by very, small visually imperceptible changes to the inputs. So this is example from the image computer vision domain. So we can train a neural network to predict an images, and then a while ago people have shown that it's very kind of simple to trick this neural network. So we can add this noisy looking thing to the image of a pig, then it still looks pretty much the same, but now the neural network will think it's an airliner. So we will use this idea in the context of individual fairness. And in order to use it, so let's just consider slightly different applications. So instead of names, we'll look at maybe more classification on sentences, where we want to decide where, let's say, a given sentence is toxic or not. So this is something that can be used, let's say, in online moderation, or these days it can be used to help make sure that the large language models are actually behaving well. So people use all those kinds of systems for alignment. So, okay, the sentence is people are Americans. So we have a model, it says non-toxic, everything is good. So now we can have an auditor, or we can call it an adversary, so which has two goals. So it wants to find the sentence x2. So all of this, by the way, happens in some embedding space, because, well, it could happen in the space of a text, but it's a little bit hard to do adversarial attacks on text. So let's say it's an embedding space. So we want to find a sentence x2 that is similar in the parametric. So dx is small. So notice that really, here instead of measuring the similarity before on images, we said we want to find an image that is similar in the sense that it's, the differences are visually imperceptible. So here, instead of visually imperceptible, we have this other notion of similarity. So, but in the end of the day, it's just a different function that measures similarity from the mathematical standpoint. And we also want the sentence to result in a different prediction, right? So instead of, before we were instead of peak predicting airliner, so here, instead of non-toxic, we want to be predicting toxic. So mathematically, it's a very similar idea after we simply replace the notion of similarity. And so here, for instance, what our algorithm can find is that now the sentence is people are gay will lead to a toxic prediction. So as long as our parametric thinks that replacing those kind of like identity tokens, so-called, replacing American with gay or with lesbian or with white, basically does not, the resulting sentences are similar. So then this algorithm will find that it will find this example x2 where, the attack is satisfied. Sort of attack is successful. So I won't go into the details of how it's done. So it's basically just the idea of adversarial training, but just a very schematic idea. So we want to train a model that is accurate on the data we have and also robust to these fairness attacks, right? So you're familiar with adversarial training literature. So there are many algorithms and this can be achieved in a variety of ways. I mean, since we worked on this, I think adversarial robustness field is moving so fast. I think they probably have like 20 new better algorithms. So I think the details are not sort of as important now. As long as we see the connection, then there are plenty of ways we can do it. So, the algorithm goes by observing some data and finding some violations of fairness. So performing this auditing step that I've just shown. And then we update the model parameters to make sure that we still predicting correctly. So prediction error is small. And then we also want to make sure that this auditor is no longer successful. And then we kind of repeat it until those conditions are met. So I will show you an example of this. So this is the demonstration we built for some user study. So this is again the toxicity prediction task, so that we just discussed. So we can measure performance of different methods. So we can train. Let's say here we fine-tune a BERT model. So we take a BERT base as a starting point, and then kind of fine-tune it to predict toxicity. So the regular model, just the empirical risk minimization, is good. So we should here pay more attention to balanced accuracy because there is a huge imbalance between toxic and non-toxic examples in the data. So the fairness is the individual fairness approach, and TFCO is the group fairness approach that's based, the idea that we can cast many of the group fairness definitions as a set of constraints, linear constraints, and then optimize with them. So, everything performs well. Of course, the regular approach has the highest balanced accuracy. So we can check the results on group fairness. So for that, what we do is we specify, so there is no clear kind of protected groups assigned to every sample in this case, but we can assign them by checking for presence of a specific word. So we take a subset of our test data, which contains, either African-American, or Black in it, and then we just filter that out. So now we have something about 6,700 samples. So we can compare different models. So the regular model has very high toxic accuracy, which, as a side note, confused a lot of people in the user study. But what it means is that it's just simply predicting, toxic for majority of the samples in this group. So that's why its non-toxic accuracy is so low. And so the balanced accuracy is also pretty low. So the group fairness method here performs the best, but the individual fairness also kind of, gets us close in that sense. And it's also a side note, but you can see how this relates to a distribution shift. So since it's also been discussed today, because imagine a test set, which is simply consists of just these samples, right? So in this case, the regular method, so it's a distribution shift, of course, right? It's a population shift. So in this case, the regular method will perform quite poorly just from the perspective of accuracy versus the methods that try to account for fairness. And in this case, they also happen to account for the population shift that perform a lot better. So finally, going to individual fairness. So the way we can check it is we can, let's say write some sentence and then put a placeholder and then provide some possible words here. So a sad day for lesbian people everywhere, a sad day for transgender people everywhere, and a sad day for American people everywhere. So these are all non-toxic sentences. So basically, but when we switch from American, transgender, or lesbian, the regular algorithm starts thinking that they're toxic. So individual fairness fixes it, and group fairness kind of partially fixes it. So we can also try, I think what we've seen. Okay, and then we can, try something like this. So, these people are bad. Okay, this is kind of toxic or negative. So everything gets it, has to be toxic. And then again, American, everything gets it is non-toxic. And then these people are gay. So in this case, only the individual fairness algorithm correctly identifies it. That's non-toxic. Okay, so this was some examples of how this algorithm trained with this adversarial robustness idea works. And so there is a lot of other, as I mentioned, adversarial robustness field is so big, and so there is a lot of other things we can do. So we can do some auditing, so basically finding, attacking essentially. So whatever is the most successful attack out there, we can use it. By the way, in auditing, we can also define some notions of hypothesis testing, so to make it a little bit, I guess, more reliable. We can apply it to gradient boosting, we can apply it to ranking. So I won't go into details, but many things can be done by just noticing this connection. And so instead, I'll talk about something that I found also working in industry, very kind of practical in a sense, right? So this is the idea of post-processing, because retraining a machine learning model is, in practice, these models, people spend years and a lot of money and time to create them. They usually have a lot of steps. It's not so easy to just throw it away and train a new one. But post-processing is something that more people are willing to try, because you don't need to change your model, and it's very simple to try. So the problem setting of post-processing is that we have some test data, we have a model, and we want to find a set of predictions. So we are simply just going to be doing surgery on the predictions that are close to the original predictions, but also fair. So again, so the inputs are just the predictions. We don't even need the model really, we just take its outputs. And then we also need to measure the fair distances for each input pair, so because this is individual fairness setting. So we can take this problem head on. And so we can say, okay, I'm going to find the set of predictions F that's close to original set of predictions, such that every pair of my test samples, the individual fairness is satisfied. So this can be done, but this is a little bit ugly. So it has a lot of constraints and can actually be pretty slow. So instead, we take a different perspective here and kind of cast it as a graph smoothing problem. So from like a graph signal processing kind of problem. So here the graph is, we have a different, let's say job candidates. So we have Alice and Charlie. So they both know, let's say Python and C++. So they're connected by this pretty thick edge. This is because they basically have the same job expertise. And so, but Charlie does get the invitation for an interview and Alice doesn't. So you can see that, okay, so this is a violation of individual fairness. So how can it be captured on a graph? Well, it is pretty simple to measure. So on the graph, there is this notion of, graph Laplacian quadratic form, which is, on the right-hand side is a nice way to write it with linear algebra. On the left-hand side is what it sort of means, which is the sum of the edge weights times the difference of the node values, basically. So here a phi of j would be the fact that, Charlie, let's say a phi will be 1 for Charlie, and the j will be 0 for Alice. And so wij will be the edge weight between the two, which will be pretty large here. So you can see how this discrepancy contributes a lot to the sum. So then we can formulate this new optimization problem where we say, okay, we still want to be close to the original predictions, as I've described, but we want to penalize the violations of individual fairness, which we now sort of penalize with this graph Laplacian quadratic form. And so it turns out that this is very simple to solve. So we don't even need to do any optimization. So this has a closed form solution. And I mean, of course, if we have a lot of data, we can write some kind of stochastic gradient version of it to be more scalable. But it's a very, very simple optimization problem to solve. And so to show that the sort of the effectiveness of it, so this is the example we saw on Twitter. So now a little bit over a year ago, so this person shared that they noticed that Distilled Bird loves movies filmed in India, but not in Iraq. And so they plotted the result for each country. So what they showed is that, okay, basically, if I take some model that can do sentiment analysis, it's not our model, that's just some pre-trained model on the internet, on Hugging Face. So they passed these two sentences. This movie was filmed in India. So the score is positive, very confidently. This movie was filmed in Iraq. The score is negative, again, very confidently. They made this whole map. So you can see, so the map, it looks colorful and perhaps visually appealing, but really what we want is this map to have one color. Because, well, we are just stating a fact where the movie was filmed, right? We are not really even discussing that is this country that makes good movies or bad movies historically. It's just simply a sentence. This movie was made in, right? So we don't really want it to receive very different sentiment scores. So and after we apply post-processing, so we can actually get it to look a lot more sort of color uniform. And so we can see, okay, sort of numbers wise. So originally the movie was filmed in Iraq. So after post-processing, it's above 0.5. So it's on the positive side. It's still kind of, not, of course, not completely, the bias is not completely mitigated. There is still some difference, but they're a lot smaller. And we can also check that, when the sentence makes sense, when it truly has a sentiment, this movie is amazing, this movie is stunning, so they still receive positive predictions. And so one interesting thing here is that, so we saw this tweet at some point, and then we're like, well, let's just try our algorithm on it. It was pretty simple. So you would, it took us maybe like some time to get the data and process it, but applying our post-processing error took us like maybe 5-10 minutes of work, because we actually just reused the fair metric from those baby names. We didn't think it would work. We just thought, okay, let's try and see where it takes us, but it was already decently good to mitigate the bias here, which was, I think, quite interesting. Okay, so just to recap, so a lot of prior work on group fairness. I mean, a lot of it is very important and useful, but there are also examples where the group fairness might not quite get us to what we intuitively would perceive as fairness. And so here, maybe in those cases, or even in other cases, we want to also consider individual fairness, which is this intuitive idea of treating similar individuals similarly. It is intuitive, but practically there are some challenges, right? So what does it mean to be similar, and how to enforce this similarity in the machine learning model? And so in this talk, we basically discussed how to make it practical through sort of mostly focusing on the algorithms. So the full pipeline here is, the step number one, you need to learn a fairness metric. This is still not a trivial step. So when I talk to people who want to apply it, this is a step that usually they need some help or guidance, because they can't just expect to press a button and get a fair algorithm. The notion of fairness is like inherently a societal notion. So we need to provide some guidance to a model. What do we mean in our society by being fair? So, I mean, we try to make this process simpler by providing those ways to learn a fairness metric from data, but the data still needs to be thought through to some extent. Then we can audit the trained ML model. So this is, if you already have a model, that's usually the case. We don't start from zero. We usually train a model to just get a good accuracy and see, okay, is this fair or not? Then if it's not, we can do post-processing. This is a very quick and easy mitigation step. And then finally, if we have patience, we can actually train a model that will be fair. And so we also have a Python library. If anybody is interested to play with it, it's just a pip install, very, very easy to use, many examples there. Okay, so do I have another like 2-3 minutes? 1 minute, okay.
Oh, 1 minute.
So I'll give a brief discussion. So recently, well, at least in industry, everybody just decided to abandon everything they were doing and start working on large language models. I think even to some extent in academia. But what's different with language models is that they are the most interesting examples of truly large models are generative. And although we had some bunch of examples from the NLP domain in this talk, they were all kind of discriminative. We take a bird, which is probably not even a large language model at this point, just a regular one. So we fine-tuned it with some classification heads. So sure, it's NLP, but it's not a generative use case. And so this becomes a little bit tricky, right? So because the distance in the space of outputs is no longer as simple, because before we could just compare predictions. So that makes the dissonant space of outputs a little bit harder to compare. Also, we can't any longer kind of work in some embedding space, or at least it's not very clear to me how. So in a sense, like the fairness with language models is hard. So I have a demonstration. I won't show it, but the idea is that we can still do auditing. So on this, and it's still kind of in a more like a supervised learning cases. So I think, broadly speaking, fairness in large language models is kind of complicated. Also, even the definitions that we have of group and individual fairness, they're not always immediately as easy to apply. It almost feels like we can apply them, but it's us just trying to apply them rather than them being the most natural ones. So I think maybe that's a discussion for, for future work. I think there's a lot of open questions there. But it's not just language models. It's basically just a generative, the notions of fairness in the generative applications of machine learning. And so I'd like to thank my collaborators, so mainly University of Michigan at IBM, who helped made all these cool looking demos. And thank you for listening, and I'm happy to take questions.
Thank you, Mikhail. Pretty cool. All the demonstrations. Any one quick question, if there is one. We do have to move on to the discussion. Anybody?
Okay.
Sorry.
If I may, one quick question. Thank you for the talk. So is this applicable? I would say you mentioned large language models. Which sort of probably deep learning algorithms is the concept applicable to? Any, say, deep learning algorithm or similar algorithms, generative models and others?
So the question is, what deep learning algorithms is this approach applicable to? So, well, anything that's classification or I guess ranking as well is fine. So because it's we can measure the difference in the output space. Otherwise, we need to figure out some new ways to measure it. That's one limitation. So essentially, any discriminative approach is fine, but generative a little bit tricky. The other part is the input space. So the way we did it so far, we took some pre-trained embedding space and then just trained in that embedding space. So which is fine. It doesn't preclude using any deep models, right? So we can take, let's say, anything pre-trained. We can even fine-tune it first if you want to. That's what we did in this in the toxicity detection task. So we took a BERT model, we fine-tuned it a little bit, and then we used its embeddings and just threw away the top layers and then retrained those with the fairness using the embedding space. But yeah, so this is with transformers. Well, I mean, BERT is a transformer model, so. But when you generate things, right, you can just average everything in the output space because it's kind of, there is all the attention going everywhere and you need it. And there is a sequential process, which is very hard to differentiate through because you create one token at a time. So it's very hard to differentiate through it, even if you could somehow attack in the input text space. So I would say with, usual networks like convolutional or whatever, basically it's fine. With transformers, where we have this sequential nature of the data, sometimes it's okay. In discriminative cases and generative, a little bit hard.
Thank you.
Well, let's move on. Thank you, Mikhail.
Thank you.
Last but not least, Razieh, floor is yours.
Cool. All right. So first of all, thanks to the organizers for providing me with this great opportunity to be a discussant, and thanks to both the speakers for their wonderful talks. So my discussion points are very high level, and my questions are just sprinkled throughout the talk. But I want to spend a few seconds telling you where my views come from. So the overarching goal of my research is to develop causal methods to better inform us with data-driven treatment interventions and policy decisions. And my methodological insights come from both machine learning and stats. And in trying to do inferences, we faced many different challenges, and the type of challenges that I think about on a daily basis is just thinking about confounding bias, especially doing drawing causal conclusions from observational data, and thinking about missing and censored data, as well as thinking about discriminatory biases that are reflected in data due to historical patterns of discrimination and inequality. And I like to think about these sources of biases and challenges using causal and counterfactual reasoning. And so I came across this algorithmic fairness world, like many, by coming across this machine bias article published by ProPublica, and they were trying to assess the Compass risk assessment tool that was being used across course in the country, and they were looking at that false positive and false negative rates for risk of recidivism, and they saw disparities and argued that that amounts to discrimination. And then Northpoint, who was the developer of the Compass tool, wrote a very long article disputing their findings and also saying that ProPublica wrongly defines measures of discrimination. So it makes one wonder why do algorithms introduce unfair biases, and what is a good measure of unfairness? And despite the promise of objectivity, algorithms rely on humans in every step of their developments, and our personal prejudices and biases find their way into the algorithm. So that makes them reintroduce, reproduce, and perpetuate these biases. And that's kind of worrisome, because then these algorithms are being deployed in socially impactful settings like healthcare, criminal justice, finance, and other areas. And we are thinking about sensitive features like race, gender, sexual orientation, religion, and other things. And there are also complications about overlapping, as Linjun was talking about, that gets into the intersectionality complications. So if you don't want our algorithms to rely on these sensitive attributes in inappropriate ways, why not just ignore the sensitive attributes? And Northpoint claimed that they didn't actually ask for race in their questionnaire, but it doesn't matter because they relied on a lot of other proxy information, asking about residential information. And we know race and area codes could be highly correlated, especially in segregated neighborhoods. And that's a map of Baltimore, Maryland that kind of illustrates this. So in my opinion, ignoring sensitive features is neither necessary nor sufficient, but then what should we do then instead? So I think in developing a framework for fairness, we need to answer three main methodological questions. And the first one is how to express fairness principles mathematically, how to modify statistical procedures to reduce these unfair effects the way we have mathematized them, and then how to generalize and deploy these modified algorithms in practice. So these three main methodological questions kind of like outlines my discussion points if I talk about fairness notions, contrasting associative versus causal notions, and talking about individual versus group level of fairness, and then talk about how to mitigate unfair biases based on pre-processing data or algorithms or model outputs, and how can we think about fairness and model performance trade-offs when we are trying to mitigate these sorts of biases. And then when it comes to deploying the fair algorithms that we have learned, what things we need to watch for, distributional shifts, and in what context we are actually trying to use these predictive models to make decisions, because ultimately that's what we are trying to use predictive models for. And then if I have time, I will talk about how algorithmic fairness can help us analyze health disparities, is an area that I'm trying to get more involved in, and I'm getting more passionate about. I'm just finish with some concluding remarks. So starting with fairness notions, there are so many different measures or associated measures of unfairness, and they are called associative because they're thinking about some independence restrictions between the decisions based on the model outputs, the observed outcome, and the sensitive group membership. There are disparate impact, demographic parity, equalized odds, calibration, and many other things. But in my opinion, these definitions are insufficient because of a few reasons. Often these definitions are tailored for a specific task, and that's usually a classification task. But that's not a big deal. But I think the major issue that I have with associative measures is that they really ignore the underlying relations between variables. All they care about often is about independence restrictions between the decisions, the outcome, and the group sensitive group membership. But they totally ignore the other variables and covariates that could exist in the model, and how these variables are actually related to the decisions, related to the outcome, and related to the sensitive attribute. So in some sense, they kind of ignore the underlying data generating mechanisms. And they're also not easily adaptable to use context-specific information. For example, they don't care often what the outcome is, how is it defined, in what context is defined. And I think a desirable definition should be context-specific, should listen to underlying causal mechanisms, and should also be non-parametric in the sense that whether your outcome is binary or discrete or continuous, you really shouldn't change your notion of what it means to be fair. So a lot of people, including myself, like to think about representing the data generating mechanisms using graphical models, the simplest form being the directed acyclic graph, and where directed edges basically represent possible causal relations, and we can read off conditional independence with a set of markup rules and deseparation rules. For example, we could have a sensitive attribute S, some, for example, race, and some outcome like risk of recidivism, and some mediators that are influenced by the sensitive feature race, for example, like criminal history, and some attributes that are kind of like baselines that are not influenced by race, for example, age. So if you train an algorithm based on this data, even if we ignore the sensitive attribute, as long as the sensitive attribute basically has a mechanism that connects the sensitive attribute to any variable that determines the model output, then a lot of the associative measures would be immediately violated. Like we wouldn't have a statistical parity, we won't have equalized odds, we won't have calibration. So that's great, but I think that's kind of extreme, because what it says is that no matter what your algorithm is, these measures are always going to be violated, which is perhaps true given how biased our data is, but there's also needs to be a chance for the existence of training a model that kind of is fair. And when we are applying these measures, they're gonna can tell us whether the model that we train based on the data that we have is actually fair or unfair, and then if it's unfair, how we would mitigate this unfair biases, basically. So the other thing is that thinking about underlying mechanisms is very helpful in trying to formalize some of the intuitions that we have about fairness. So a lot of you have come across this legal code in hiring discrimination, where the judge is asking, would the employer have taken the same action had the employee been of a different race, and everything else had remained the same. So if we collect relevant information, we would have the DAG on the right-hand side with sensitive attribute being race, outcome being hiring, and some mediators, like some characteristics that are influenced by race, for example, education, experience level, and some baseline factors. So as Mikhail was saying, so a hypothetical experiment that could convey an answer to this this question is name swapping experiments, when we are changing resumes of people with Caucasian sounding names and changing the names to African American sounding names, and then submit the resumes and see whether the hiring decision changes or not. And if you do it several times, we get a sense on average of whether there is discrimination or not. What's very interesting about this is that thinking about the underlying mechanisms, what we are really doing with this experiment is just kind of manipulating the direct effect of race on hiring status, and we are leaving the indirect effect through other characteristics of the resume, like education and experience level, intact. So that kind of using causal language, causal and counterfactual language, this experiment kind of corresponds to quantifying the direct influence of this perceived race on hiring status. So that's kind of neat, but I also want to emphasize the importance of context on why we should incorporate that when we are thinking of defining what it means to be fair. So this is an auditory example when the outcome is still hiring status, and sensitive variable is now sex, and we have a mediator that kind of indicates some physical fitness according to some physical tests. So we all agree sex shouldn't directly influence the hiring decision, but depending on whether, for example, we are hiring a firefighter or whether we are hiring an accountant, then the effect of sex through this physical fitness should be different, should be interpreted differently. So if you're hiring a firefighter, for example, the effect of sex through physical fitness is something that might be relevant and permissible and fair. But if you're hiring an accountant, then using physical fitness as a predictor should be treated differently, in the sense that, okay, we have to make sure that the effect through this physical fitness shouldn't be relevant for hiring decisions of an accountant. So this kind of like very simple toy example illustrates of why definitions really should be context specific. Listen to what the context is, what the outcome is, and what the underlying relations between variables are. Okay. And it could be that we could have more, so it's easy to talk about this when we have like 4 variables, but we know reality is not as simple as that, and we could have very complex data generating mechanisms. But the thing is that this complexity is kind of force us to keep domain experts in the loop. And this is another toy example where the outcome is health risk assessments or health risk scores, and the sensitive attribute is race. And we have now 2 possible mediators that are influenced by race, for example, whether patients have access to insurance or not, and whether there are comorbidities and complications and due to some clinical history information. So thinking about risk calculations, like we shouldn't, maybe in a specific context, shouldn't think about the effect of race directly, or the effect through whether patients have access to insurance or not shouldn't be relevant and permissible. But maybe the effect through complications is something that is relevant and should be permissible. So at least it helps me quite a lot to think about the effect of the sensitive attributes on the outcome through different mechanisms, to kind of like illustrate a little bit better of how we are treating different variables and different covariates that exist in the model, and are we treating them the same or differently depending on what mechanisms are we considering to be permissible or relevant. And so that then the question is, how do I come up with all these underlying mechanisms? So we could account for unmeasured variables in the model that shouldn't really scare us. But the point I'm trying to make in this slide is really that we must, it's not that we should, we must keep experts in the loop. And we as researchers, I don't think we can do it all to claim that we have a fair algorithm to make fair decisions. So the other point is about the individual versus group level fairness. And as Mikhail mentioned, population level notions are very popular, and they are popular because they're just like easier to work with. And when we are even in causal settings, when we are thinking about the effect of a sensitive attribute like race on risk calculations, we are really thinking about a population level effects. For example, thinking about the total influence of race on an outcome, we want it to be 0 or null depending on what the scale is. So we are really comparing potential outcomes if the race was Caucasian versus if the race was African American, and evaluate this on a population level. So that's what the expectation is for. But then individual level criteria are more desirable, but more difficult to ensure because there are a lot of complications. At least from a causal point of view, there are many issues with the identification. So if you're thinking about individual level causal effects, we are thinking that, okay, this potential outcome should be the same for this specific individual I if they were Caucasian versus if they were African American, and we never ever observed both of these potential outcomes. So this sort of notion is never going to be identified. And in terms of estimation, it also creates a lot of complexities because it's just like doing estimation and inference with one sample size, basically. Still a lot of progress has been made in terms of thinking about individual level fairness. And the core idea is that algorithm should treat similar individuals similarly. And the similarity is based on some measured covariates X. But I think unless we believe that all individuals in the population can be really uniquely characterized via this vector of variables, we are still doing a population level definition. And it's very hard to believe that this variable, this vector X actually is rich enough to uniquely characterize individuals. So what we could be doing is thinking about, for example, conditional effects when we're trying to see whether the causal effect is null in a population of people for whom X takes value little x, for example. Whereas the individual level effect is still thinking about the causal effect for a specific person I, for example, for Alice, and we want that effect to be 0. But by thinking about similarity measures based on this measure covariates X, we are still thinking about a population level quantity. And so maybe calling it the subgroup level is a better term than the individual level, but it's not really about the terminology, it's just like about the implications of it, whether we are claiming we are doing individual level fairness or versus something different. And the second point is that similarity is often said is based on some measured covariates X, but which covariate should we include in X? So should we include all possible variables that we have, or variables that are influenced by the sensitive attribute, or variables that are not influenced by the sensitive attribute? But I think variables should be treated differently depending on whether they are really downstream effects of the sensitive attribute or not. Like, for example, in this simple example where outcome is hiring and sensitive variable is race, and the mediator is education, and my baseline is age. So should I match individuals based on age, or based on age and education, or based on education only? But the thing is that if I want to include education is a downstream effect of race. But my question would be, how should I account then for the historical biases that exist due to segregation and a lack of access to a high quality education system for everyone? So maybe person I in the minority group would have had the same education had they been had they have access to the same educational level of quality, basically. So then what I'm thinking is just like, maybe we should really match based on age and a counterfactual version of education, of thinking, the two individuals would have been the same if they had access to the same resources, basically. And the third point is, as Mikhail also mentioned, it's just like there are too many free parameters to play with. But the question is, what are some of the guidelines for practitioners in selecting the right similarity metric? And it's not that we are claiming that the algorithm is going to be fair for a wide variety of similarity metrics. That's often even not possible due to a statistical conflict. But then what should we do when we face this choice of picking a similarity metric to match people, basically, based on that? I think moving on to the second point, okay, maybe you disagree that causal notions are in some sense just bridging some of the gaps that exist in associative measures. But if we have a pre-specified notion of fairness, then the question is, how do we actually mitigate this biases basically from our algorithms? And typically there are three different ways that people approach it. It's just by, for example, pre-processing the observed data. Like if we want to satisfy demographic parity, we would learn a representation of data that is independent of the sensitive group membership, and then train this model that we are interested in based on this new representation that we learned. And the second kind of approach is post-processing the statistical output, as both Linjun and Mikhail mentioned. We can first train a model and then post-process the output to satisfy this pre-specified notion that we have. But the third type of approach is to just retrain the statistical model subject to our fairness constraints. So that would entail solving a constraint optimization problem. And the constraint optimization problem would, for example, if we have a well-defined likelihood, we can solve a constraint MLE problem where the constraint ensures that the unfair effects basically are absent. I've adopted this approach myself and never thought about adopting the pre-processing and post-processing approach, because this looks very easily generalizable. Like it's agnostic to kind of what the fairness notion is, what the constraint is. You can always frame the problem as a constraint optimization problem, but it's because maybe I don't work with LLM models and I don't have to worry about retraining this models often. But I wonder, like, what would be other advantages of actually using post-processing methods over this constrained learning? Is it really just about the fact that it's just hard to retrain the model every time, or is there something more? And I think like like post-processing approaches are also just like tailored to a specific task with a specific notion of fairness. So I would assume there are a lot of complexities there as well. And I think that for framing the problem, mitigating this bias as a constraint learning problem is kind of like, it makes it intuitive to think about trade-offs between model performance and satisfying this fairness norms. I think of satisfying fairness norms as hard constraints, so they're always going to be sacrifices for model performance. But if I want to study this trade-off, I can set up my constraint optimization problem by really thinking about putting lower and upper thresholds on my constraint and try to see how my model performance changes if I change this, basically play with this thresholds. So I wonder, like, how can I actually set up like this sort of a study to analyze these trade-offs more naturally with post-processing approaches. So moving on to the third step is that, okay, so I picking one of these approaches, I made sure that my algorithm is fair, but then the question is, how do I deploy it basically in practice? And one issue that we have to always watch for is the distributional shifts, as Linjun mentioned. It's just if the test distribution and the train distributions are different, they would have a lot of trouble. But what I have a quick comment here is that even if the train and test distributions are the same, we would still run into issues surrounding this distributional shift. So how could that be? So sometimes, in order to satisfy these fairness norms, we can think of actually moving whatever statistical task that we have to a fair distribution. So we have the unfair distribution P, and we have the fair distribution P star, and we can define it, for example, as something that is a distribution that is as close as possible to the unfair distribution, but it's a distribution that satisfies our fairness constraint. But then, if I learn if I do my statistical task under this fair distribution, then if I want to deploy the model that I train, I have to be mindful that my samples actually come from the unfair distribution. So there needs to be a mapping of samples from the unfair distribution to the fair distribution. So to kind of like account for this equivalent distributional shifts problem. So that's my quick comment here. But then the second point in this section is that it's just, all we want to do, or all I care about, is how to use predictive models for decision making. And there could be three different scenarios. One is what's called the predictive decision support, where the decisions are solely made based on the model outputs. So this really constitutes a big portion of fairness literature. And so the second type, which is kind of more realistic, is what's called what I'm calling the prediction assisted decision support, where we are actually using predictive models as just like informing our decisions, but our final decision is really based on incorporating some presented facts and some personal judgment. So it's more realistic, but it's also just like much harder, almost impossible to ensure fairness in the settings. Like, who knows what goes on in a judge's brain if they're using the Compass risk score to just like inform their decisions, but they're making their decision based on other information as well. But then there's a third type of decision support that we could be thinking of, is just is having a notion of utility or reward function in mind. So what is the ultimate goal of taking an action and making a decision? So it's often to kind of optimize for some final outcome that we are interested in. So the judge, for example, wants to decide on incarceration by thinking about optimizing public safety, or an employer wants to make the hiring decision by optimizing the company's revenue or something like that. But this setting, I think it's just more realistic than the first one, but it's also something a little easier than the second one, that we can make some progress to ensure that we have this sort of fairness constraint satisfied. So this is a quick toy example in child welfare. So we receive a call from to the Child Protective Services, and certain information gets collected, some sensitive attributes like race, and some baseline factors, and some variables that are kind of influenced by the two. For example, whether there is incarceration history and whether family members receive public assistance or not. But then given all this information, the call screener needs to make a decision, for example, whether they should dispatch a caseworker or not. But the idea is that only cases with substantial potential risk to child welfare should be prioritized. So in order to basically minimize some negative outcomes, like avoiding child hospitalization and separation from parents and things like that. So the thing is that all these information that are used to calculate risk score and make the decisions depend on sensitive feature or some proxies of it. So then there is this natural worry that these would be dependent on the sensitive features in inappropriate ways. But what we want to do is just like make the decision by making sure that, for example, certain unfair mechanisms are absent. We don't want race to directly affect the chances of dispatching a caseworker, and we don't want race to directly affect the chances of child hospitalizations. But maybe there are other different mechanisms that are also we want to avoid. So that's kind of like also highlights again the importance of thinking about mechanisms. But the point I'm trying to make here is that, okay, so when it comes to this kind of decision-making scenarios, there could be different sources of biases that we have to watch for. And one is about what I call the retrospective bias, and that has to do with the bias that exists in historical data that is used as input to learning procedures. So that has to do with how my sensitive attributes actually affects the final outcome or the final utility function that I have in mind. But then there's also a second type of source of biases, then calling the perspective bias, and that has to do with the functional form of the policy itself, that how it depends on the sensitive attribute. So that has to do with thinking about the mechanisms through which the sensitive attribute can actually affect these decisions. And I wonder, like, if I want to actually avoid the predictive decision support and think about this sequential decision making by trying to maximize or optimize for some utilities, how the frameworks that were discussed and earlier can be really adopted to incorporate this kind of constraints. And so just like to some of my questions is just like asking about fairness questions, that we have strong opinions about causal versus authoritative measures, and should the underlying data generating mechanisms be relevant or not, and how to keep experts in the loop, or we as researchers can do it all on our own, and whether context is important or not, and if it is, how should we incorporate it into our frameworks, and what do we actually mean by individual level fairness, and how do we deal with different choices that we have to make when it comes to a specific task. And then when we are talking about mitigating bias, thinking about the generalizability of our approach, and thinking about the trade-offs that we have to make between satisfying these constraints versus not losing too much performance. And then lastly, thinking about the deployments of the model, of how do we think about mapping samples from the fair to unfair, or from unfair to fair distributions, and then how can we actually incorporate different sources of bias in terms of retrospective or prospective biases that could exist into our frameworks. Do I have time? I kind of skip over this.
Yeah. Let's just stop so that we can have Mikhail and Linjun also. If you could just maybe this list of questions you had is a good place to for them to chip in.
So happy to.
Thanks, Razieh. That's great. Yeah.
Thank you, Razieh, for the discussion. So should we provide some comments? Or?
Yeah, that'd be good. If like maybe 5 minutes or so, if both of you split among you, so 2 minutes each or something like that.
Okay, great. Yeah, I can start. Thank you again for the discussion. I think very interesting point. So, well, I wanted to comment on the sort of statistical issues with considering individual fairness, because it's kind of a per point notion, right, instead of a distribution or population notion. So this can actually be avoided. So if you recall the 2004 study, right, the final conclusion was that the resumes with wide sounding names received 50% more callbacks, right? So this is kind of a decision on average across the population. And so I didn't go into the technical details, but we can define so-called the distributional individual fairness, which we've done in our works on this, where instead of looking at the neighborhood of an individual, we look at the neighborhood of data distribution. So we can say, I want to make sure that, this notion of like, okay, similar individuals. So let's say I can take my data distribution, I can define a Wasserstein ball around it. And then I can say, okay, for every distribution within my Wasserstein ball, I want to make sure that the similar individuals receive similar treatment. So this theoretically gets around the problem. Practically, it actually results in a very similar algorithm as if you were to kind of approach it directly. But theoretically, it helps to maybe adjust some causal notions as well. So also a comment on the individual subgroup level fairness. I think that's, I mean, in my sort of, it's not, I think, very rigorous, but I would say that the subgroup level fairness, as the subgroups become more and more fine-grained, it's basically kind of a way to interpolate between the group fairness with traditional demographic groups and individual fairness, where every group is an individual. So I think I would agree that perhaps some very appealing notion of fairness lies somewhere kind of in between those two extremes, because maybe we want to consider like some notion of groups, but relatively fine-grained. So now in terms of the different choices of similarity measures metrics, I think it's of course a problem, but when we do group fairness, we also pick one of the many definitions of group fairness. And we know that, there's like tens of them. And we also have results saying that they cannot be achieved at the same time. So we also make choices there. And I think all these choices are very important. It should be consulted with sort of domain experts. But I guess my point is we always make some choices here. And even with group fairness, it's not just one notion of fairness really, right? It's 10 definitions which are somewhat incompatible in most cases. My last point was measuring the post-processing, the trade-off. So at least in our work, this is achieved by assuming that the original predictions of the model are good. So then we can trade off between, some fairness regularizer and then how close we are to the original predictions. So this allows us to trade off kind of the accuracy of performance and fairness in the post-processing context. And yeah, I guess it's more of a practical concern, but talking to if you come to someone who like runs, let's say, a system for doing some kind of healthcare decision making, and then you say like, well, your system is unfair, just throw it away and retrain. They maybe not so easy to convince them to actually try out something you're suggesting, or maybe it would be a lot of work on your end to actually do it. So post-processing is more like, okay, we can quickly try it and kind of show you what we can achieve, and then maybe they become like more sort of willing to explore further. But I think that the retraining kind of is the final ultimate step that should be done. And yeah, so I also wanted to second the sequential decision making. I think that's very interesting, and I think that's very much kind of avoided in the current literature, because anytime we decide to do some interventions of fairness and maybe change how we do some healthcare decision choices or loan approvals and so on, this has some effect on the population, and this leads to a new population, and we don't really consider that very much in the current fairness literature. But I think that's kind of maybe the right way to think about reducing the biases in the long run. Okay, and yeah, thank you. Those were some comments I had.
Thank you.
Linjun?
Yeah, because of time, maybe let me have a very quick comment. Yeah, so I very, very agree, say, defining fairness based on, say, maybe causal DAG is a very interesting idea. And actually in the literature, there is some notion called, say, counterfactual fairness defined in this way. But one of the major concerns from the algorithmic fairness community is that typically those DAGs or some causal frameworks relies on certain assumptions, for example, the structural equation model or something. And they are afraid, say, if you need to assume assumptions to ensure a fairness, then what if, say, basically no real data satisfy the exact condition? So but then this means the fairness definition they don't make sense, or something like that. So this is one of the main criticisms I saw from the algorithmic community, fairness community. So I just want to have maybe I just want to have maybe more of your opinion on this issue, because I'm not a causal expert, And I'm easily convinced by this type of argument from the CS community. So I don't know if you have any opinion on this. Just like, what if the assumptions used in causal model are violated?
Yeah, I mean, like there's also this whole research around doing, trying to learn the underlying mechanisms, like, or the causal DAG, like from the graph, so doing like data-driven structural learning and causal discovery things. But also just like trying to validate some of the assumptions we make in the causal DAG by just like talking through the experts. And that's also part of like why I emphasize that like keeping experts in the loop would also be helpful in that regard as well. It's just like try to falsify or verify some of the assumptions that we are making. And I just like about that, like there's also I gave a short fairness tutorial at JSM, and this is the link to it. So just like we talk about it quite more, like in terms of causal notions and different causal DAG models to do fairness around fairness frameworks. Yeah.
Yeah, great, thanks.
Yeah, that's a very useful source to look at. Thanks, Razieh.
Yeah, I will definitely check it out.
Actually, quick, because Razieh brought this up, and I kind of agree with this like optimization framework of thinking about things, like viewing it as a constraint. What was your guys's remark on this? If you have like a quick 30 seconds, do you view that as somehow problematic if you kind of think about it as an optimization problem?
I think it makes sense. I mean, everything is kind of an optimization problem with constraints, as long as you know.
Yeah, but I guess it's
can be general enough.
I do like it as being kind of one thing as opposed to a sequence of steps. I do like kind of a one step. Here's the optimization algorithm you'd want to solve, and of course now you can go to town about this and figure out how you can solve this. But is there?
Well, I think this approach says we first agree on some notion of fairness, which is the function that defines the constraint.
Okay.
So this would be either some group fairness definition or the individual fairness metric. And then after that, it is the optimization problem with constraint. So I think if you want the notion of fairness somehow to be adaptable, then the constraints themselves will have some parameters. So that makes it maybe a little bit harder. And also sequential maybe frameworks potentially not as easy to formulate as kind of one problem, like maximum likelihood with constraints. But I think the kind of the standard settings where we care about like the current system and the current population, after we agree on notion of fairness, I think it always can be written as a constraint optimization problem.
Yes.
Yeah, a quick comment is, so one of the challenges, typically the fairness notion is non-convex. So it's quite hard to directly solve the non-convex optimization.
Yeah. No, I understand that, yeah. And appreciate it. Yeah.
I mean, something else we looked a little bit into is that the group fairness, a lot of it is kind of data-dependent constraints. So there is also a notion of generalizability, right? So like, will this same constraint continue to hold out of sample? And then, you know, even if there is no distribution shift, there is still a notion of how well does it generalize. So that's maybe something else to consider.
I see. Cool. Any last final comments by anybody? Also in the audience, if you have questions, thoughts.
Stop sharing it.
Maybe I start with few and hopefully others join. I like this discussion by Razieh. So my question also relates to causal aspects. In terms of the fairness, this distinction between group, subgroup, and individual fairness seems similar naturally to individual treatment effects. And I was considering, is there any issue if the individuals in your population are very heterogeneous? And related to this, frequently, I think also in the causal inference literature, the problem of treatment effect heterogeneity is solved using Bayesian approaches. sometimes could Bayesian approaches be used using fairness and machine learning?
I don't see why not. Like, it's just like, especially if you think about the constraint optimization problem, like I mentioned, we can do a constraint MLE problem, but that can be very difficult, requires a lot of parametric assumptions. But then one way to do this is just like frame the problem as a Bayesian problem, where we are really trying to sample from the posterior distribution, but making sure that the samples actually satisfy the constraints. So one naive thing to do is to do rejection sampling, but that may take a long time to achieve the constraint. But then that's just like one way to do it. Maybe there's just like more better ways to incorporate Bayesian inference into the framework. Yeah.
Thanks.
Anybody else? Okay. If not, thank you all for participating, for the audience for coming, and for the two wonderful speakers and the discussion. I think it's all good to maybe for all of us to look at Razieh's nice JS tutorial. Good for us to learn about kind of the causal perspective too. And yeah, I feel like I learned a good amount. So this talk will be available on YouTube. So for those of you who want to see it again, maybe give us a couple of days and you'll find it on YouTube. Maybe I think if you have put your name on the sign up sheet, we'll send you a link to the YouTube recording. Anyways, thank you all, and hope to see you in our next webinar. Thanks again for everybody for the discussion.
Thank you very much.
Yeah,
Thank you
for
so much. I
organizing.
enjoyed it a
Thank
lot.
you.
Yeah.
Bye.
Have a good rest of your day.
Thanks.
Bye.
Thank you.
Bye.